Hello everybody, as Josue introduced me, I'm Mohammad Sohrabi. I'm a postdoc at UC Merced, and over there I do modeling. Of course, not fashion modeling. I do hydrologic modeling. Don't get me wrong, I know how to catwalk, but I still have doctorate degree. And you better call me doctor. Just joking. Jokes aside, this is my first time here in this meeting, and I realized that most of talks and sessions are related to reservoir modeling, managed aquifer recharge, sigma, and in general water resources planning and decision making. But before we do any of this or address any of these, we need to know how much snow we have in the mountain, when it melts out, and what portion of it goes as runoff, evapotranspiration, and groundwater. Or for future water resource planning, we need to know how increases in air temperature changes precipitation phase and snow melts timing, and how these changes impact soil moisture dynamics, groundwater recharge, evapotranspiration, growing season lengths, and the timing and magnitude of peak flows. For all these reasons, we need to do headwater modeling. And this is our framework that we are working at UC Merced. As you can see from the diagram, we couple a process-based snow model with the USGS PRMS model, and we turned off the snow module of PRMS model. And it is noteworthy to mention that this coupling substantially improved the performance of the PRMS model. Such modeling framework is very beneficial, and we can use it for reservoir modeling, the output of the model, of course, for the reservoir modeling, water resource planning, watershed restoration, and decision making. But there are some challenges with this kind of modeling. One of the main challenges for this kind of modeling is the quality of meteorological inputs in the mountainous regions, in particular precipitation, which I will talk about it in the following slides. The second challenge is calibration of a rainfall runoff model, such as PRMS that we have in our framework. I had a poster presentation about the solution we have for this issue, and I will, for the sake of time, I will shortly talk about some of the points in this slide for those of you who haven't seen the poster. So what is the common approach for calibration of a rainfall runoff model? What is it?
Use a point.
Yes. Yes, that's right. Using a discharge, change parameters of a model to fit and match the estimated discharge with data observed. Using a point-based measurement such as discharge for calibration provides high values for model performance evaluation indices for discharge, in expense of increasing uncertainties in other hydrological fluxes, such as evapotranspiration, which is an important hydrological flux for watershed restoration, forest fires, or vegetation distribution and mortalities. To solve this issue, we introduced an approach for a spatial calibration of a distributed model by using ET, by using a spatial distribution of ET from normalized difference vegetation index, which provide us a realistic calculation of water balance for each grid cell. I can talk about more details if you haven't seen the poster after the talk. And for the sake of time, I'm going to go back to the issue related to quality of meteorological inputs. Most of biases in headwater modeling comes from this uncertainties in the spatial distribution of precipitation, which is mainly due to lack of precipitation gauges at high elevation. Even if we have precipitation gauges at high elevations, they undercatch precipitation, particularly solid phase of precipitation. To mitigate the impact of this issue on snow modeling or headwater modeling, we combine observation from precipitation gauges with that of snow pillows observations. As you know, snow pillows do not measure precipitation. they record changes in the snow water equivalent, and because of that we considered any increase in snow water equivalent as amount of precipitation in that day, and combine that with observation with precipitation gauges and force the modeling framework with that. This figure compares the estimated snowpack with that of observed. The top figure shows the snow water equivalent average over all snow pillows, and the bottom one shows average over all snow courses. As you can see from the figure, we have substantially better estimate for snowpack when we combine observation from precipitation gauges with that of snow pillows. This figure shows the estimation of snowpack across the basin, and you can see that we have substantial underestimation at high elevations when we don't add precipitation information from high elevations. And this underestimation causes large uncertainties in calculation of other hydrological fluxes. For instance, surface water input is underestimated by on average 27%, which by itself brings large uncertainties to estimation of flow that reaches through the dam, or to the estimation of flows that we want to use for groundwater banking or manage aquifer recharge. With this point, I'm going to finish my talk.
Questions for Mohammed?
Have you or your group explored the remote sensing techniques for snow or snow water equivalent or snow depth for the headwaters? Or are you mostly focused on the modeling framework?
We are mostly focused on modeling framework, or doing modeling, but we will use eventually, because we're going to use this headwater modeling framework to prepare it for near real-time estimates, and eventually we're going to use remote sensing data to more validating our models.
So do we have 27% more water than we think?
Yes, climate change impacts solved. Just add some snow pillows.
I'll catch you at the reservoir. So more questions for Mohammed? Yeah, Hubert?
Well, I think calibrating on discharge is still very valuable, because with evaluation of the evolution of the groundwater elevation, you get a good mass balance. What you are referring to is the uncertainty to differentiate between precipitation and evapotranspiration.
So what we observe, and I think I've seen in a couple of other publications, that when we only use, we can use still multi-objective calibration approaches, but when we use point-based measurements, like potential evapotranspiration along with discharge, we changes parameters of the model in the way to have a favor for that, to get better feeds, better Nash-Southfield coefficients, rather than focusing on getting a realistic water budget for each grid cells.
Yeah, I agree with that. And basically what I'm saying is that the discharge has the advantage that it integrates everything above it in the watershed, so it's a very good
yes.
Index.
That's right.
But that kind of approach doesn't tell you the difference between what is precipitation and evapotranspiration. They only give you the difference.
Yes.
And but you know that difference. You don't know which ones was precipitation, which one's evapotranspiration. So what you're doing is to try to distinguish between the two, and that's very valuable.
Thank you. Yes, that's right. So the discharge shows the average over all the basin. So it tells us it's a very valuable index that shows the average across the basin, but doesn't show when we need a special resolution for all hydrological fluxes. It doesn't give us any information about that.